Let's restart. Oh, by the way, I upload the homework, so hopefully you'll see my my announcement. So basically, that'll be our last homework. Okay, I think there will be like 3 problems. You can, as we said before, so I don't think you can do all of them now. So you should be able to do all of them after Monday, next Monday. So I think our last class will be next Wednesday, right? Yeah. Okay. So we have 4 more classes to go. All right. So let's review what we covered in the last lecture. So basically, in the last lecture, we talked about map and the ML decision rule, and then we talk about how to choose basis functions, right? So basically, we didn't talk about exactly what is the criterion to choose a basis function in very detail, but we try a few bases to see whether they work or not, and what are the differences, right? So let's see. So for map and ML decision rule, so the derivation is as follows. So basically, this is a map rule, right? So I've seen that before, and here, so basically, you would need to know the PDF, right? And the PDF of R given SI ascent, right? And then, so we need to know the prior probability of SI ascent, right? In general, normally, so we don't know this part, right? And the safe condition, the safe assumption is that we assume the probability of S0 ascent and the probability of S1 ascent are the same, right? They equal to 1/2, and then so then we don't need to consider this part because it's a constant number, right? Then we just need to consider the first part, right? The first part will give us the ML rule. It's called maximum likelihood, right? The reason it's called the likelihood is that, so note that this is a PDF, right? It's not a probability, right? So when we pick a L to maximize that, we didn't maximize the probability explicitly, right? Eventually we maximize the probability, right? But from here, so it doesn't maximize the probability. So what it maximizes is the PDF, right? Then that's why it's called likelihood, right? The PDF is called likelihood normally. But it's not a probability, okay? And given this, we can get this formula, right? They're equivalent, right? So this basically means that we need to find a region where this guy, if this guy is bigger than this guy, then we say it's S0 ascent. And if this guy is bigger than this guy, then it means that S1 ascent, right? So if we sketch it, then basically we look at this figure, right? So basically this is the PDF of R given S0 ascent, and the green one is a PDF of R given S1 ascent, right? And from here we can see in this regime, so it's all the black is bigger than the green one, right? Then it means that in this regime, so we're gonna decide S0 ascent, right? And if we're in this regime where all the green one is bigger than the black one, then in this regime, so we're gonna decide S1 ascent, right? And the mean here is given by the square root of the energy of the signal, transmit signal. Okay, it's square root of E and minus square root of E, right? In this case, you can see, so equivalently, it's a threshold decision rule, right? So it basically means that if R is bigger than gamma ML, so it basically means that S0 ascent. If R is less than gamma ML, it means that S1 ascent, right? So it becomes a threshold decision rule. And we derived this rule explicitly in our last lecture, right? So basically, if we take a detailed look at this, so write down the PDF, right? And from the formula we wrote before, we could get this kind of distance decision rule, right? So basically, it means that if R is closer to S0 compared to the distance between R and S1, then it's gonna decide S0 ascent. Otherwise, S1 ascent. Right? It kind of makes sense, right? So the reason we have that is because the form of the PDF of a Gaussian distribution, right? So ML rule become a minimum Euclidean distance rule, right? And then from this distance decision rule, we can get threshold here, right? So basically, in this case, if you consider ML detection, the threshold is always the average of S0 and S1, right? So remember that. So this is always the case in this case, okay? So we derive that explicitly and on the figure, so it basically means the average between this guy and this guy. So we have minus square root of E here, we have square root of E here, then our gamma L would be 0, okay? So which kind of coincides with our intuition. Okay, so now the next question is that, okay, so we try a f of t, right? Try a base function here, and it works pretty well. But in general, how can we choose f of t? Okay, so those are the two conditions we want to satisfy, right? The first condition is that we want to make sure that f of t, we can use f of t to represent our signal as 0 of t and as 1 of t explicitly, right? And in the sense of a zero error energy, so basically it means that, so we want the mean square error to be equal to 0, okay? And the other thing is that we want the basis to be minimal. Basically, it means that we cannot achieve zero error energy with fewer functions, right? For example, in the case of the antipodal signal, so one basis is enough, right? But in some cases, the one base may not be enough, right? We may need more than one, right? Okay, and here's an example we give in class. So basically, if you consider this is the waveform of S0 of t, and this is the waveform of S1 of t, and then we can show that we need two bases, so one base is not enough. So what we try is the same as before. So we use the normalized version of S0 to be our one base, right? And then we try, okay, so if we do the inner product between S1 and F0, so it becomes a 0, right? It means that we cannot use F0 to represent S1, right? So it doesn't work. Then we came up with another base. So what we tried is that we use a normalized version of S1 to be another base, right? Because these two functions are orthogonal, so this basis worked, okay? And so basically here, what we do is a mapping here, right? So we map our signal on both F0 and S1, see what are the results, okay? So, if we have more than one basis functions, so basically now what we get is not a scalar anymore, right? It's a vector, right? It's kind of a projection of a signal of an original signal on these two bases, okay? So what we get is that if we project our signal as 0 on F0 and F1, so what we get is this one, right? So it's the square root of E and 0. So basically, given this point, right? If you consider it's a function space, so the x-axis is represent F0 of t, and the y-axis represent F1 of t, right? So this would be the coordinates, right? So here is square root of E, and on the other coordinate will be 0, so it's a 0 on the other coordinates, right? And similarly, if we project our signal on project our S1 of t on both bases, and then we can see that in this case, so the x-axis, which is the axis of F0, so that will be 0, right? But on the other hand, so on the axis of F1 of t, it will be square root of E, right? Which corresponding to this number, okay? And now we can see, okay, so now we have a signal space, so we call that constellation, okay? And so if we, those are basically the 2 points here. And if we compute the Euclidean distance, remember, so after this mapping, right, and then we're going to use this number to make our decision, right? So this still follow Gaussian distribution, right? So our decision rule would be still the same. It would be a Euclidean distance-based decision rule, right? Then what matters is the distance between these two, right? So basically, if we take an average of these two, right, if it's on one side, it would be F1, on the other side, it would be F0, okay? So now we can see the distance here now is square root of 2e, right? Versus the antipodal case, where the distance is 2 times square root of e, right? We can see that this orthogonal signaling would not be as good as antipodal signaling given the same energy of each signal, right? So the antipodal case is one is square root of e, the other one still on this direction, right? It would be negative square root of e, right? That one would be better, okay? So this one is not as good as the other one. Yeah, but when we do orthogonal signaling, that will be the case, right? So is that clear? Okay, so basically, when we decide, the signaling, so we want to, decide on this domain, right? Once we determine how many bases we're going to use, then we're going to decide the locations of each point here, right? So that's called constellation. Okay, And so we didn't go over this explicitly in our last lecture, right? But we have notes on this. You can look at my notes. I have a detailed computation there. So basically, if we try another base, right? So we assume S1 and S0 is the same as before. Let's try this base and that base, right? You can see that they're orthogonal, right? Because it's kind of time division, right? There's no overlap between this and that, so we can verify they're orthogonal, right? So given this, we can basically see. So if we do the same projection there, so we can see the coordinates of S0 is given by this, right? And the coordinates given by S1 is given by this. Yeah, I missed a bracket here. Okay, and if we draw that on the constellation on the new basis, so we're going to see that. So for the first one, so it has this amount on F0 tilde, and have this amount on F1 tilde, right? And so this point represents S0, and similarly, so this point represents S1, right? And for these 2 points, you can see, so this will give you the magnitude of that, or the square of it will give you the energy. So energy is still E, right, which is the same. But now this would be the location of the new signal. So you can see compared to what we got before, right, it's kind of a rotation of that, right? So because we used a different basis, and the distance between these 2 points would still be the same, which is square root of E. Okay, and that will be the same for all the signal that has this orthogonal signaling. Okay, that clear? Right, so if you have doubt for the computation of that, just check my notes. So it should be clear. Okay, so those are what we covered in the previous lecture. Okay, that clear? Any questions? Okay, great. So let's continue. This is our lecture 35. Okay. 34, 35. 34, 35? 35. Okay. Yeah, made a mistake here. Yeah, should be 35. Okay, great. So today, yeah, we're going to see a little bit on how to find the basis f of t, right? So we're not going to detail of that, so we don't have the time. But I'll give you a direction on what is the idea to look at that, and then we're going to look at more general case, right? Because so far for the detection, so everything we have been looking at is the binary case, 0 and 1, right? So what if we want to transmit more digits, right? And then what should we do? What will be our decision rule, right? So basically, I say how to get or compute the likelihood functions if we have more basis functions, right? So, and then after that, so we're going to answer one question we asked in the beginning of digital communication, right? So we have two important metrics to talk about. So one metric is called the spectral efficiency. Yeah, how to spell efficiency? It's spectral efficiency. Okay, and another important metric is called energy efficiency, right? Probably we don't have time to talk about that. Let's see how far we can go for today. Yeah, probably we can finish the second part, hopefully, right? And then in the next class, we're going to talk about spectral efficiency, and then we'll talk about energy efficiency, and then we're pretty much done. Okay, and yeah, let's see. We don't have much left. This is the first one, right? First one is that, okay, so we need to know how to find the basis, right? So we need to know how to find a basis. Okay, so basically, we have tried different bases, right? We're kind of using the ad hoc method to find the basis, and that is pretty much you need to know exactly, right? In your homework and in your exam. So yeah, that is what you need to do, right? Just try normalized version of one signal, see whether it works or not. If it doesn't work, normalize the other one, right? See whether it works or not, right? But in general, that would be not the method, right? What is the rigorous method to find a basis, okay? Yeah, let's see how we can do that. So basically, the way to find a basis is like to find a spanning set for our signal space, right? So basically, we need to, in order to find a base, then we want to find a so-called spanning set. Spanning set for our signal space S, right? So now we see, one example is that S is S0 of t or S1 of t, right? But in general, it could have multiple signals, right? Okay, and so by the way, so the number here is called the modulation order, right? I think you have this kind of question for your homework. Okay, so the spanning set here, so basically means that it's not exactly a basis, but it could be a basis. So meaning that, so it's like a basis, but may not be minimal, right? So it's like a basis, but may not be minimal, right? So it basically means that, so we can represent each of signal R Si of t as a combination of all the basis function, right? So basically, if we denote our basis function as Fn, right? So we may have n of them, let's say n from 1 to capital N, and each of them will have a coefficient in front of it. We denote that Sin, right? So those Sin is basically what we get after the inner product. Okay, so yeah, we can have this formula. But it's called spanning set, right? But if it's minimal, meaning that n is the smallest number to make this possible, then it will be a basis. Okay, and there are, in general, there are two approaches to find the base. So one approach is called the universal approach. Okay, so for the universal approach, it basically means that so we can use some fixed function to represent a base. Okay, so in our approach, so the basis depends on our function here, right? So for example, in this case, if it's antipodal, we use S0 normalized version of S0 for a base, right? So it depends on our transmitted signal, but it is possible that we use just general function for this, right? So probably we want our basis to be orthogonal. So we're going to explain why we want that, right? So if we want our basis function to be orthogonal, can you come up kind of a base, right? A set of functions that are orthogonal to each other. Have you seen this kind of function in your other classes? Or kind of in this class as well, right? So we may think about, how about the Fourier series basis? Okay, if you think about that, right, if n goes to infinity, then it'll be a series, right? So we can actually use this guy as, we can use the Fourier series basis as this guy. Okay, so the first, so it basically means that it does not depend on Si of t, right? So for example, we can use our Fourier series basis for this. Or our Fourier transform basis for this, right? Right, so basically it means that ej2 pi ft, something like that for our basis. Okay, so we can do that for different frequency. Okay, and if you want to use that, so our S of t has to be periodic, right? Otherwise we can't. All right, so this is one approach, right? But what is more popular is the approach that we introduced before. Okay, so we're gonna figure out our basis given what we're transmitting, right? What kind of waveform that we're using. Okay, so this approach is called set specific basis. Okay. So basically, so in this case, we can guarantee that our function has a zero mean square error, means zero error energy. Okay, and so the way to find this is there's an approach, there's an algorithm. It's called the Gram-Schmidt algorithm. Okay, so basically the idea is similar to what we introduced before. So we're starting from, for example, S0, right? We assume that the normalized version of S0 would be one of our bases, right? And then we're going to compute the error, right? If we just use one base to represent our signal, right? And then we're going to compute the error of using this base to represent S1. Okay, if the error is 0, then we're done, right? But if the error is not 0, then we're going to normalize the error to make it as a new base and so on. Okay, so that will be the approach. Okay, so but yeah, we don't need to compute that. Just remember, there's an approach to compute the specific basis here. Okay, so we're not going to talk about that in very detail in our class. Okay. All right, so yeah, just want you to know we have two approaches to figure out that. And given this, so now what we're going to see is that, how to compute the likelihood if we have a lot of basis functions. Okay, let's see how we can do that. Okay, how to get likelihood if you have more basis functions? Right, let's see now what are the differences, right? So we studied explicitly that we have when the number of bases is 1, right? Have one base function, right? So now we want to have multiple basis functions, right? Let's see what are the difference. Right, we kind of have seen one sort of example before, right, or two. We have two bases instead of one, right? When we have one basis, so basically we use this PDF to make our decision rule, right? So basically from here we can derive the map rule and the ML rule, right? Just using this base function. But now, so since we have multiple bases, so multiple basis functions. Okay, so now we still have our we still have this distribution, right? But now this distribution, instead of scalar, right? If I have one base, so R is basically scalar, right? But now, if it's a multiple bases, so now R would be a vector, right? Do you remember what I've seen before? Right, so maybe it worth to show this again. Yeah, like this. Right, so basically in this case, so we have two basis functions, right? So in this case, so this is our S0 and S1, right? Remember, so R is what we have after after the inner product, right? So yeah, let's see. R is nothing but given by this, the first row, right? So R equals to Si plus the Gaussian noise, okay? And the way to obtain R is nothing but we compute the inner product between the received signal and R of t and our basis, okay? So that is basically our R. R equal to Si plus the noise, okay? And when we have more than one basis, so basically what we got is, for example, it's something like this, right? And this is our S0. Now it's a vector instead of scalar, right? If I have more than one basis, now I have two bases, right? And similarly, S1 is equal to this vector plus a noise vector, okay? So now our received signal R become a vector instead of scalar. Does that make sense? Right, okay. So if that makes sense, then I think we're okay. So this is what we have shown here, right? So this R here will have only one base function. So this R is a scalar, it's a random variable, right? But for this R, so this is a random variable. Yeah, this is this is a random vector. Okay, but the way that we're trying to compute is exactly the same, right? We just need to compute an inner product between our received signal R of t to each of the bases to get all the coordinates. Okay, so yeah. Okay, so yeah, let's write down what we're going to do here. So basically, what we're going to do here is as follows. So basically, yeah, let's write it here. So now, we assume we have m signals to send. So our set of transmitted signal given by this, S0 of t, S1 of t, up to Sn minus 1 of t, right? We assume we have m waveform to send, right? So yeah, let's recall. So now if I have m waveform to send, so how many bits we can transmit per waveform? So for each one, how many bits we can transmit? Right, we have m of them, right? If m equal to 2, we have S0 and S1. So how many bits we can transmit? 1 bit, right? 0 and 1, right? So now let's say we have m waveforms. So how many bits we can transmit? Say again? N over 2? N over 2. What is n?
Oh, n over n.
Huh. Yeah, not exactly. Yeah, let's say if m is 4.
Actually, yeah, it's like log.
Exactly. Yeah, so yeah, it's called MRE communication. So yeah, we mentioned that before. So basically, the number of bits we can transmit equals to log base 2n. Right? Hopefully, you still remember that. Okay, so now using the Gram-Schmidt approach, for example, so we can find the basis, right, which is denoted by the set of f. So we assume that the basis denoted by f sub k of t, and we assume k is from 0 up to n minus 1. So assume that the number of basis functions is capital N, right? And we say it's a basis, right? So then n is the smallest number, right? So we also define this capital N, so which is the number of functions here for a base, right? So this is a basis, right? So we define this n as a dimension of S. Okay, so assume this. We call this n as a dimension of our signal space of S, right? So if S is antipodal, then the dimension of that is 1, right? And if it's orthogonal, then the dimension of that is 2, right? So in our previous example, right? So this is called the dimension of our signal space of S. Right? And in addition, we can see that, so this is always less than or equal to the cardinality of S, right? Which is n, right? So n is always less than or equal to n, right? For example, again, in the antipodal case, so our m is 2, right? We have S0 and S1, but the dimension of our signal space is just 1, right? So in the orthogonal case, the dimension, the cardinality of our signal space is still 2, but dimension would be 2 because we need to use 2 basis functions to represent that. Okay, so yeah, this is called dimension. So this is the cardinality of S. Yeah. The relationship between A and M. Okay, great. Now let's introduce some notation. So now let's say SI is sent, right, as before. Okay, so now we need to compute the inner product between SI and each of the bases to get the received vector R, right? So basically, yeah, let's introduce some notation. So basically, we let Sij equals to the inner product between Si and Fj of t. Okay, and all these elements here, so this form of Si, which is a vector, right? Si basically is a vector of Si1, Si2, up to Si what? The number of basis function, right? As capital. Yeah, I need to. It should be from 0 to n minus 1. Sorry for that. S0, I0, I1 to I n minus 1. Right? So this is the notation here. Okay? So now let's see how can we design our receiver. Yeah, let's draw it here. It will be pretty much the same as before, right? The only difference here is that we need to project off our received signal on all the bases, right? So now this is our received signal, R of t, right? So that equals to, remember, S whatever I of t plus R noise N of t, right? And now we need to do a product between this guy and all the bases, right? So basically what we're going to do is that, so first we need to do a multiplication with the first base, F0, And then we need to do an integral of it, right? And in this case, we're going to get R0, okay? And then, similarly, so we're going to do the same thing for the second base function, and then do the integral. So get our R1, right? And we're going to do that with all the bases, right, until Fn minus 1. And then we do the integral and get Rn minus 1, right? And then collect all this R, so we get our received vector, right? So one bar here, I denote this as vector, right? And this vector consists of R0, R1, up to Rn minus 1. Okay, and then we're going to make our decision rule. Okay. Yeah, so this is the receiver structure. So before, when we talk about the antipodal case, we just have one of those, right? But now we have multiple of those, right? So this explicitly equals to R0, R1, up to Rn minus 1. Okay, very nice. So now basically, all this operation doing, all this inner product, it's kind of projection. So we project R of t to this vector, right? So this is basically a projection to our signal space. Right, and this signal space is determined by the basis functions. Okay. So now what we need to know is basically, remember before when we have only one base function here, so we characterize fr given Si, right? So we characterize the PDF of this guy, right, or this distribution, right? So now what we need to do is we want to characterize the PDF of this, right? So which is the adjoint distribution given R is a random vector. Okay, so this is what we want to do, right? And we're going to do this now. That clear? Okay, let's see how we can do that. So basically, so we know R of t is a Gaussian distribution, right? Because we computed this before. So R of t is a Gaussian process, right? And after all this linear operation, so for each of them, it will be a Gaussian distribution, right? So for each, let's say, if we denote Ri as the inner product between Rt and Fi of t, right? We know each R of this, given which one is sent, so it will be a Gaussian distribution, right? So now the difficulty is that, so what are the, so whether those Ri's are related or not, or correlated or not, right? So they are all independent, or they are correlated, right? If they are all correlated or dependent, then this formula can be complicated, right? So we want to characterize that, right? Ideally, I think what we want is that we want all of these elements, R0, R1, up to Rn minus 1, to be independent, right? So that would be an ideal case, because in that case, so this formula would be much easier to see, right? And we're going to see the benefit of it. So now we're going to find a condition when, so all of these random variables would be independent. Is that clear? So that's our goal. Okay, so let's try to characterize it. Okay, yeah, so yeah, I will change it to J, because we're going to compute RT, the inner product between RT and all of this, right? So I denote that as Fj here, and so let's assume that Sj of t is sent. Okay, so now we're going to see what Rj is. So basically, Rj is the inner product between Rt and Yeah, fjt, right? So then what we get is that we have sj of t plus nt, and then this, right? And then as before, so we're going to break it into two. Yeah, so we need to use a different notation here. Let me see. Yeah, probably. Yeah, let's keep the same notation. Yeah. Because I use a j here, right? So I use a j here. Then this should be I guess. Yeah, I don't need to change it. I think I'm still using I here. I think that'll be better. Yeah, because for each signal S of j, we need to compute the projection of this with all of the bases, right? So we need to use a different notation here. Okay, great. And given this, so this would be equal to Sj T, the inner product between Sj and Fi. Fit, right? And then add the inner product between n of t and fit, right? Very nice. And then, so now we assume Sj is sent, and then this is inner product between Sj and Fi. So we use the notation here of Sji, right, to denote this inner product. And then we add Ni, so that's the notation of this inner product. Okay, and so we cannot compute it before, right, but with only one base function. Okay, so we know this the distribution of Ni, right? So Ni is a Gaussian distribution with 0 mean and n naught over 2 for the covariance, for the variance, right? Remember, n naught over 2 is nothing but the power spectral density of n of t, right? So hopefully you could connect what we have learned before. Okay, so now so this is deterministic, right? So we don't have a problem for that, right? So if Ri is a Gaussian distribution, and then it'll be the mean, right? So, and we know each of Ri would be a Gaussian distribution with mean, yeah, maybe let me write it down. So for each Ri, so it will be a Gaussian distribution with mean of Sji, and this is the variance, right? We have seen this before, right? But what is not, we have not seen before is that now we need to characterize the joint distribution of this random vector R here, right? So besides the marginal distribution of each individual R, so we need to characterize the joint distribution, right? Or the covariance matrix, right? As we said, so what we want is that we want all of them to be independent, right? So if they are independent, then we just need to multiply each marginal distribution, then we can get the joint distribution, right? So now we want to see under what condition all the Ri's or Ri's are independent, right? And we know this part is deterministic, right? So equivalently, to make Ri to be independent, we need to make sure all the n's here to be independent, right? So what we want is that we want Ni and Nj independent. Right, this is what we want. Okay, and we know Ni and Nj's are Gaussian distribution, so this basically means that, or vice versa, so double direction, Ni and Nj uncorrelated. Right, if we can show they're uncorrelated, then we're fine, right? And uncorrelated basically means that the expectation of Ni times Nj equals to the expectation of Ni and Nj, right, and equal to 0, right? So this is what we want to show. If we can show that, then we're done, right? So now let's see how we can show it. Of course, this is for I and j, they're not equal, right? So if they're equal, then of course it not be 0, okay? So let's verify under what condition, so this will be true, okay? So let's compute it. So expectation of Ni and Nj, right? So that equals to nothing but the expectation. So we're going to use this to compute it, right? So basically, that is the inner product between T and Fi of T dt, and multiply another inner product between Nt. Yeah, let's use another dummy variable here, right? So because we use T here, then we use U, and Fju du. Okay, so let's compute it. So similar to the trick that we used before, so what we do here is that we're gonna group it into double integrals, right? They're just independent integral, can make it as a double integral, right? And then we bring the expectation inside, right? So basically what we have is that we have expectation of Nt and Nu, right? So those are the random variable. And then we'll have Fit times Fj u dt du, okay? And now, so we know this, right? So what is that? It's the autocorrelation function. Okay, so this is nothing but n naught over 2 delta t minus u. Okay, and given this, so we could integral t first and then integral u, or vice versa, doesn't matter, right? So basically, if we integral the u first here, so we have this multiply that, then we just need to replace u by t, and then we're done, right? So basically, yeah, this would equals to expectation. Oh, no expectation anymore. Yeah, I moved that inside, right? We don't have this expectation. Right, so basically what we got here is that, so we take this n naught over 2 out, and then use the sampling property of delta signal, and then we can get Fit multiply Fjt dt. Okay, and this is what we get. And as we said, right, so what we want is that this guy equals to 0, okay? And so what we want is that, so this would be, yeah, maybe, let me see, yeah. So this, I say equal to 0 if I and j are not equal, right? And if ij is equal, right, then it will be basically just ni squared, right? Ni squared, because the expectation of ni is 0, ni squared will be just the variance of it, would be n naught over 2, right? So basically, if they're equal, we want that to be n naught over 2. Okay, and we have n naught over 2 here, right? So basically, the condition for this guy is that if I and j are not equal 0, not equal, it's 0. Otherwise, it will be 1, right? So by using the Gram-Schmidt approach, so we can make sure, so when I and j are equal, this will be 1. So when I and j are not equal, basically, if they are different bases, so that guy equals 0. So basically means what? Means the inner product between Fi and Fj, so there is 0, right? So this basically means they're orthogonal to each other. Okay? So now we can see, okay, if we want all the r's are independent, so the only thing we need to guarantee is that all the bases are orthogonal. Okay? Right? So we could have, non-orthogonal bases, that's no problem, but it will give us some trouble for this distribution, right? If they're orthogonal, then so they're all independent, then we can easily write down the joint distribution. Okay? So now we know all the r's are orthogonal, are independent, right? Then let's say given Sj is sent, so basically what we get is Fr given let's say given Sj, right, sent. So that'll be nothing but the product, right? Because they're all independent, so then we have a product between S0. Yeah, I use an I here. Okay, let's change it to I. Si sent. Now we have Si here as a vector to n minus 1. So because all the r's are independent, then we just need to write the joint distribution as a product of each marginal distribution, right? Given by this. So remember, so the notation here basically means the jth component of Si, okay? And each of them is just the marginal distribution, but the marginal PDF. Okay? Yeah, I think we're out of time. So next class, we're gonna go from here, and then we're gonna see how we can make our decisions. Okay, so now we kind of know how to compute our likelihoods. Okay? Yeah. Thank you.